Okay, so hello everyone. Well, in this video, I wanted to make a introduction into what is sensorization and data analysis. In particular, I want to first discuss what are some of the sensors that we can use to monitor the state of a machine, an electrical machine like an electric motor. And then I want to discuss a little bit about what is the process or the preprocessing steps that you need to perform to the data collected from a sensor in order to send that data into a computer. So first, I want to discuss why we need sensors in an electric motor. And we can classify this need in 2 points. No, first, we want to control the speed and the angular position of the motor. Now, in order to monitor if the speed is reaching the velocity that we want, we need to monitor that speed. And to do that, we can use a sensor that is called an encoder. But also, we are interested in detecting faults in an electric motor. And these faults can be related to excessive current, insufficient torque. Maybe we are overheating the machine due to the increasing temperature inside it. And well, overheating is a concern because if you increase too much the temperature inside the machine, you can melt the insulations in the windings, and that can produce short circuits, or you can produce the magnetization in the permanent magnets of the motor. And what is the magnetization? Is basically the reduction of the magnetic flux of the magnets in the machine. And if you reduce that magnetic flux, you will be reducing the machine's torque capability. So the machine becomes useless because you cannot produce movement with it. And here in this pie chart, what I'm showing you is some of the most common causes of faults in an electric motor. The major cause of fault is the overloading, no? That is also related to overheating the machine. What is overloading is basically means that we are demanding too much torque to the machine, and also that is associated with certain amount of current, and the excess of current in the machine can produce the overheating of the windings or the overheating of all the other components inside the machine. So that is why we need sensors like a temperature sensor, not to monitor the overloading of the machine, or maybe we can monitor the current that the motor is demanding. Also, we can have faults related to rotor failure, bearing failure, the old age, contaminants. Also, you can have misalignment in the shifts of the motor, or there can be other electrical faults like open circuits or short circuits in the machine. But the major concern, as we can see in this graph, is that the overloading is the major cause of faults in any electric motor. So that is why we need to monitor the state of the machine in terms of mechanical elements, in terms of electrical components, in terms of thermal components, in order to prevent those faults. And well, to do this, we can use sensors. No, recall that a sensor is basically a device that responds to a physical stimulus, and based on that physical stimulus, we can produce an electrical signal that we can record in a computer, no, or in a microprocessor or microcontroller. And well, in the case of the sensors that we can use to monitor the state of the machine, well, we can use temperature sensors, Hall effect sensors, accelerometers and gyroscope sensors, potentiometers and encoders, no? For example, a temperature sensor will allow you to monitor the temperature state of the machine. The Hall effect sensor can be used to monitor the speed of the motor, or also you can use a Hall effect sensor to monitor the current that the motor is demanding. Accelerometers and gyroscopes are also used in order to monitor the vibrations of the system, in particular mechanical vibrations. And the potentiometer is a variable resistance that we can use to control the power that is supplied to the motor. And finally, the encoder is a device that is basically a disk that is coupled to the shaft of the motor that we can couple to it and monitor the revolutions per minute, no? Of the shaft of the motor. And well, first I want to discuss some of the sensors that we can use, no? In particular, the ones that I described previously. First, we have temperature sensors. And a temperature sensor, in simple terms, is basically a device that detects a change in temperature in the environment and produces an electrical signal. Typically, that signal can be a voltage or a resistance change. And the most common types of temperature sensors are the thermocouples and the thermistors. What is a thermocouple? Essentially, the idea of the thermocouple is that you have a junction of two metallic objects that are different. First, in this graph, you can see that we have chromel and alumel, and we have a junction of these two metallic objects. So when you apply heat to this junction, you can produce in the other side of the circuit a voltage difference, okay? And this voltage difference is proportional to the difference in the temperature in the junction of the two metallic objects. And this is related to an effect that is called the Seebeck effect. Okay, the Seebeck effect basically describes this phenomena in which you have the junction of two metallic objects. When you apply heat to that junction, you can produce a voltage difference in the other side, and we can use this principle in order to detect temperature changes based on electrical changes in the voltage. And well, here, what I'm showing you is a diagram that, well, it's a GIF, an animation, no, that basically describes this behavior, no? You can observe here that we have again two materials, material P and material N. So when you apply heat to this junction of these two materials, you can see that there is a current flow, okay, or a flow of electrons, no, that is moving between this conductor, and based on that, we can measure the voltage drop in this part of the circuit with a voltmeter. And here we have a picture, no, of the of a thermocouple. So in general, the idea of the thermocouple is that we can detect um, change in temperature by measuring a voltage. There are other devices that are called the thermistors. The thermistors, as the name implies, basically consist of sensors that change their resistance when you change the temperature around their environment. Here is a picture of a thermistor. No, it's essentially a resistance that it changes its resistance, its electrical resistance, based on the changes of temperature. And we have two types of thermistors. We have the negative temperature coefficient and the positive temperature coefficient thermistors. What is the difference between them? Well, the difference is illustrated in these two graphs. For the negative temperature coefficient thermistor, you can see that as you increase the temperature, you are decreasing the resistance, and you have a negative slope. But in the case of the positive temperature thermistor, um, you can see that as you increase the temperature, you're increasing the resistance of the sensor. So there is a trade-off between these two variables. But also you can notice that the relationship between temperature and resistance is not linear. No, we have this like exponential decay or growing exponential behavior of these two sensors. No, when we analyze their temperature and resistance relationship. So the challenge of using this sensor is some kind of calibration, and also that you need to map this nonlinear relationship between the temperature and resistance. So, well, if you want to avoid this behavior, there is other type of sensors like the LM35, developed by Texas Instruments, that has the following package. And the advantage of this temperature sensor is that it has a linear relationship between the change in temperature and the change in voltage. In fact, it has a linear slope that, well, is described by this value that is 10 millivolts over Celsius degrees. So there is a proportional change between the change in temperature and the change in the output voltage supplied by the sensor. Also, another advantage of this sensor is that it has a very low power consumption and that the transfer function of the sensor is linear. No? So there is another advantage of the sensor. And well, we have another device here that is called the potentiometer. The potentiometer is basically again a variable resistance, but we can change mechanically. If you move a little bit this screw that we have here, you can change the resistance of the component. Typically, in order to power these devices, you need to connect this terminal to positive, this terminal to negative, and if you measure here the voltage, you will see change in voltage because we are changing the resistance of the components. So in essence, we are not measuring the resistance, but we can measure the voltage changes due to the change of resistance of the component. And they can be used for performing, for example, voltage dividers. You can use these sensors or these devices to change the brightness in televisions or use as a dimmer of certain lights. And also you can use these devices as faders in audio equipment. In fact, if you have used a guitar amplifier, for example, an electrical guitar amplifier, the knobs that the guitar amplifier uses are based on potentiometers, okay? So typically they can be used as as sensors that can be used to control other components or to change the intensity of certain signals, no? So, well, here, let me erase all of this. Um, this is the diagram of the potentiometer. The one that you will be using for your project is this one, the panel mount potentiometer of 10 kilo ohms. There are different types of potentiometers with different values. Basically, the value refers to the maximum resistance that the potentiometer can have. For example, here, these potentiometers of 10 kilo ohms, that means that you can change the resistance between 0 and 10 kilo ohms. There is also other presentations like the trim pot that is shown in this in blue in this picture. And well, you change the resistance of this trim pot by using a screwdriver in order to change the resistance, and you need to couple the screwdriver in the top of the potentiometer. And these are the functional diagram. No, this is at the end a schematic representation of what is happening inside the potentiometer. Basically, you have the contacts between two resistive materials. No, and when you move this contact, you are changing essentially the resistance. And this is a schematic symbol, no, of the potentiometer that you can find in many electric circuit design softwares like Tina or Multisim. And we'll hear some applications, no, of the of the potentiometer. Okay. And well, another type of sensor that you can use to monitor the state of an electric motor is the encoder. The encoder is basically a disc that is coupled to the shaft of the motor, and we can monitor the revolutions per minute of the shaft of the motor by using this device. Also notice that we have certain holes in the perimeter of the disc, and we are using these holes in order to detect pulses that are measured by um, infrared sensor. And based on the pulses produced by the infrared sensors, we can monitor the revolutions per minute of the encoder. And well, other sensor that you can use to monitor the current in many electric circuits is the Hall effect sensor. The Hall effect sensor is based, or it works thanks to the Ampere's law. Remember that the Ampere's law states that when you have a current that is flowing through the conductor, you can produce a magnetic field around it. So the Hall effect sensor is taking that physical principle into account to measure the voltage produced in a magnetic core that is placed around the conductor. So the magnetic field produced by the current flowing through the conductor will produce a voltage in this magnetic core, and we can measure that voltage in order to detect the current changes. Remember that the Ampere's law also states that the magnetic field produced by a current flowing through the conductor is proportional to the current. So that is another way in which we can monitor the current in a motor and also in many electrical devices. Okay. And finally, well, this sensor is mainly used to detect like electric faults. Okay, also you can use a potentiometer or a variable resistance to detect voltage changes. But if you want to measure mechanical vibrations in a machine, well, you will be using an inertial measurement unit. The inertial measurement unit has two sensors. Now we have an accelerometer that is basically measuring the acceleration in the three axes of a 3D body, and in the X, Y, and Z axis. And also we have a gyroscope that is measuring the angular position around the X, the Z, and the Y axis. And this is an example of an accelerometer, and you can see that when he's moving the accelerometer, we're also moving the cube in this animation. And this sensor is widely used when you want to detect mechanical faults related to vibrations. For example, you can detect vibrations in a drone, in an electric motor, in the bearings of a machine. So it's widely used when you want to detect mechanical vibrations. For example, also you can monitor the vibrations of a suspension of a vehicle, or maybe you want to measure the vibrations of your combustion engine motor, no, using this sensor. Okay, so this is all related to some of the sensors that we can use to monitor the state of electrical machines. But and there are many type of sensors, no? I don't want to discuss too much into the detail of all of the sensors that you can use and all of the brands and all of the sensor types that exist for each of the sensors that we discuss, because I want to concentrate in something that is a little bit more general but also more important. That is, what is the process of data acquisition? Okay, how can I ensure that I am measuring the data collected from the sensor into a computer? No? What are the considerations that you need to take into account to transfer the information from the sensor into a computer and then store that information for later analysis? So, in order to understand the process of data acquisition, first we need to define what is a signal. Okay, so a signal is basically the measurement of a physical phenomena over a period of time. Okay, for example, in this picture, what I'm showing you is what are the changes of temperature over a period of time for the windings of a permanent magnet synchronous motor. In fact, well, this is data from a real motor that we used in the past, and you can observe how the temperature changes occur over a period of time. And that is basically a signal, no? It's a time series, no? It's a measurement about the dynamics of certain system that is evolving over time, no? And we have a record of that. And well, we can classify these two, the signals in general, into analog, also called sometimes continuous, and digital signals. Okay, typically we can say that all of the signals that exist in the environment are analog or continuous signals. And when you transfer those signals into a computer, we convert them into digital signals. Okay. But we can have like a more technical definition, no, of an analog signal. An analog signal is basically um, a signal that can take any value. Okay, the signal can take more than two values, more than three, more than four. No, it can take 1, 2, 3, 4, 5, 6, 11, 0.37 values. No, so there is no limit to the values the signal can take. Typically, those values are within a certain particular range, but within that particular range, the signal can take any of those values. Examples of it are the voltage, the temperature, and the pressure. And these analog signals are characterized by the level, the shape, and its frequency. The level basically refers to the values that the waveform can take. The shape refers to the form of the signal. For example, here we have a sinusoidal waveform that has a sine form, okay? And also we can characterize the signal by their frequency. For example, according to this image, we know that this waveform has a frequency of 0.2 hertz. And in order to know what is the frequency of any signal, we can use the Fourier transform. Okay, we can apply the Fourier representation of this signal in order to understand what are the frequency contents of these measurements. Because typically, many measurements can be characterized, or many natural processes can be represented by its frequency spectrum. Based on that, we can design filters in order to remove the noise from the signal. We can compress the information of the signal and so on. And well, the other type of signals that we have are the digital signals. Contrary to analog signals, digital signals can only have two values that are typically referred as high and low. High and low basically refers to two voltage levels. Okay, the low level is typically associated with a 0 volts voltage, and the high level is associated typically with a 5 volts level voltage. But the main fact is that these digital signals can only assume two values, okay, or two voltage levels, and that's it. That's why we call these two values the states. Either the signal is in the off state and the on state. And um, also we can characterize these digital signals by their rate. Okay, that is basically like the frequency at which they are oscillating, no, between the off and on state. And now that we know what is the signal, um, how can we take the signal and transfer that into a computer? And well, we need to perform many steps. One of these is the signal conditioning. But what is signal conditioning? Imagine that you have data from a sensor, no? That is the physical phenomena that you want to measure. But when you're using a sensor, well, the sensor is basically an electrical device, no? Or an electronic device that is susceptible to interference. You can have electrical or magnetic interference in the sensor that could introduce some level of noise. And the noise is basically these random oscillations that the signal has in the high frequency spectrum. Now, there are very rapid oscillations that are changing very drastically the form of the waveform that we want to measure. So the idea is that we typically want to remove this noise. How can we do that? Well, in this signal conditioning step, we can remove that noise by using electronic filters, or also we can use digital filters. That means that we can program a computer in order to reduce the level of the noise present of the signal. Also, another part of signal conditioning is that we can amplify the voltage levels of the waveform. For example, there are sensors or there are physical phenomena that have a very low amplitude. So we want to increase the amplitude of that measurement in order to send that information to a computer, because sometimes computers cannot read very small voltages. So maybe we need to amplify the voltage levels of the waveform in order to transfer the information into a computer. So signal conditioning is basically the task of amplifying and also filtering the information from a sensor, and then we can transfer that information into a computer by using an analog to a digital converter. The idea here is that we are taking samples at a certain time interval of the signal that we want to measure, and but in this way we are discretizing the signal, and those discrete values, no, that are basically performed like in steps, are transferred or are converted into a binary representation that can be read by a computer. Many computers, for example, the audio card of your computers, or the Arduinos, for example, or any data acquisition system, uses analog to digital converters to transfer the information from the physical sensor to the computer. And also we need to define another parameter that is called the sampling time, okay? The sampling time basically refers at the rate at which the computer is taking the measurements from the sensor and storing them in their memory, no? Or converting them into a binary representation. So we can convert this discretization into a binary number, and then with those binary numbers, we can develop a software application based on the readings that we have. So first, I want to discuss this step, no, about signal conditioning, because typically we will always assume that the sensor maybe is corrupted by certain level of noise, or maybe the amplitude of the sensor needs certain amplification or maybe attenuation that we need to perform on the signal to read them correctly. So in order to amplify the signals that you want to measure when they have a relatively small amplitude, is to use an operational amplifier. The operational amplifier is basically a circuit, okay, that has the following diagram, no, in the form of a triangle, in which you have this point and this point represent the power supply of the operational amplifier. This pin represents the output voltage of your sensor or the thing that you want to measure. And we have two terminals, the positive and negative terminal, that is where you introduce the input waveform that you want to amplify or attenuate. This is that picture of the operational amplifier. It's basically a chip. There are many presentations. This is like a relatively small presentation of an operational amplifier, and is one of the most commonly used in many audio amplifiers, for example. Well, you can use this type of device. And well, this is the connection diagram that basically relates these pins or these legs of the chip with the diagram that we saw in this part. Okay, some of these pins are associated with the positive and negative terminals, other ones are associated with the power supply, all other ones are not connected. So this is the basically the connection diagram of this chip. And well, you can use, if you arrange some resistance in a particular way in the operational amplifier, you can generate a device that can amplify or attenuate the input signal. For example, if you want to produce what we call a non-inverting amplifier, um, well, what you need to do is um, to arrange a resistor R2 and a resistance R1 in this position. In this case, R1 is connected between the negative terminal and the ground terminal, and R2 is connected between the output voltage and the input voltage. And also we have the in, that is the input voltage that you want to amplify. And in this case, it is connected to the positive terminal. So when you have this arrangement, what you can do is to amplify by a certain amount the output voltage based on the input voltage. This basically represents the transfer function of this operational amplifier that is also referred as the gain. So this equation basically relates the output voltage divided by the input voltage. So this means that you can amplify the input voltage by this factor R1 plus R2 divided by R1. Um, and in this way, you can increase the voltage level of the waveform. We will see an example of this in the following slide, but this is basically the gain or the amplification factor of the input. Um, and we will see that effect at the output of the operational amplifier. Also, we call them non-inverting amplifier because this means that if you have a positive voltage at the input, you will have a positive voltage at the output. If you have a negative voltage at the input, you will have a negative voltage at the output. And the inverting amplifier has the opposite behavior. When you have a positive voltage, you will get at the output a negative voltage. When you have a negative voltage, you will have a positive voltage. Okay? And well, I think that's it. And well, the inverting amplifier has a different configuration. You can see that the input voltage is connected between R1 and the negative terminal of the operational amplifier, and R2 is connected between the negative and the positive terminal. And also we can say that the positive terminal is connected to ground directly. And I think that's it, okay? And well, also the amplification factor is obtained by dividing R2 over R1. So the greater the R2 and the lower R1, you can have a greater gain factor. So these are the two circuits or the two configurations that you can use to amplify the waveform when you have a relatively small amplitude and the input. Okay. So this is an illustration of this. You can see here that I have here connected in Tina the diagram of the non-inverting amplifier. In this case, I set R1 equal to 1 and R2 equal to 1. And here we have R1 equal to 1. So if you add 1 plus 1, you will get 2. And this means that the gain factor of this operational amplifier is 2 multiplied by the in. That means that the input voltage will be amplified 2 times. And we can see this effect in this graph. Here the green line is the input voltage that has an amplitude of 1 volt, but the output voltage that is like this red or brown signal is has an amplitude of 2 volts. because we are amplifying the signal by the factor of 2. So that is the usefulness, no? That you can amplify the voltage levels of your input signal by the factor that you want. And this is useful when you have measurements from a sensor that have a relatively small amplitude. Also, we have the inverting amplifier. Again, you will notice that the amplification factor is the same. We have 2 over 1. And this is multiplied by the input voltage. Okay. And well, also we have a negative sign here. And the reason for that is that this configuration will change the polarity of the input voltage. And that is also appreciated in this graph. When you have a positive voltage, you are getting a negative voltage that is amplified by a factor of 2. Okay, so you can also notice that the amplitude is of -2 because we are working with this non-inverting amplifier that has a gain factor equal to 2. Also, we have here another positive voltage, but at the input we have a negative voltage because we are using this non-inverting amplifier, no? That is changing the polarity of the output voltage based on the input voltage. And well, I think that's it. And what else we have here? Um, well, I think that I will stop the video for now, and then I will start continuing with this idea of noise because it's a little bit more abstract. So you can take a break and then we can continue.